we are going to start talking about carbohydrates, which are often referred to as sugars and starches. As with any molecule, the type of functional groups in the molecule are going to dictate the types of chemical properties and chemical reactions that those molecules can undergo. With carbohydrates, the types of functional groups we're going to encounter is going to be multiple hydroxyl groups. Again, recall hydroxyl groups are OH groups. And you're going to see that throughout your carbohydrate molecules, there are going to be a lot of these groups attached to your carbons. This is going to make it very water soluble since these OH groups have the capability of hydrogen bonding with water. You're also going to see that there are going to be aldehydes and ketones, which are also going to dictate the types of chemical reactions they can undergo. Some other features of carbohydrates, yes, they are sweet tasting, but their sweetness can actually vary greatly. Some may be very, very sweet, while some are just moderately sweet. And lastly, they are very polar compounds, again, in large part due to those OH groups, those hydroxyl groups, and therefore they're going to generally have very high melting points. So in this video, we are going to learn how to classify carbohydrates and how to name them using just general categories. And then we are going to start looking at how to draw these structures. We're specifically going to look at Fischer projections. And in order to do this, we're going to have to learn a new type of stereoisomer, which is going to be the enantiomer. In a separate video, we are going to look at these Haworth projections. All right, so let's talk carbohydrate classification. They can be classified into three broad groups. The first is going to be your monosaccharides. Mono, again, this just means one. So this is going to be your basic building block of carbohydrates. So this is as small as you can get in just one basic building block of a carbohydrate. These monosaccharides, we are going to see in a separate video that the reactions they can undergo are oxidation and reduction. But right now, we are just concerned with learning how to classify them. So this is an example of a monosaccharide on the left-hand side. This is going to be what we call the acyclic structure or an open chain structure. This is where the Fischer projection formula is going to come in. And then these open chain molecules can actually cyclize. They can undergo cyclization. And so this is what we are going to refer to as Haworth projections, which we will talk about in a separate video. But the point here is that a monosaccharide can exist either as an open chain or it can exist as a cyclic structure. And we are going to learn how to interconvert between the two. Then we have disaccharides. Di means two. So this just means that you have two monosaccharides joined together. And you're going to see that they are joined together specifically by this carbon here that sits to the right-hand side. From this oxygen, you're going to see that that carbon there is the one that's going to be forming those bonds. We're going to learn some new functional groups here. There's going to be the acetal and the hemiacetals. And then we're going to learn that that carbon that does the bonding is going to be our acetal carbon. So we will talk about those in the video where we talk about the Haworth projections. We're also going to see in a separate video that the reactions that these undergo are called synthesis and hydrolysis reactions. Synthesis is where the bond forms and hydrolysis is where the bond breaks. Lastly, we have polysaccharides. Poly means many, and so this means we're going to have more than two monosaccharides bonded together. And here is an example of such a structure where you can see that you have several different monosaccharides bonded together. This is an example of the polysaccharide that we call starch, and we will talk more about that in a separate video. Okay. So again, the three classifications for carbohydrates are either a monosaccharide, where we're just talking about one unit of a carbohydrate. Disaccharide is when two monosaccharides are bonded together. Polysaccharide is when three or more monosaccharides are bonded together. Let's talk naming monosaccharides. So the first thing you're going to want to do is specify the carbonyl functional group. So all of your carbohydrates are going to have a carbonyl group. It's either going to be an aldehyde or it's going to be a ketone. So here with glyceraldehyde, you're going to see that here at the top, this is a classic aldehyde functional group. And when your carbohydrate contains this functional group, we call that an aldose. When it contains a ketone, as shown here with dihydroxyacetone, this is going to be called a ketose. This OSE ending is classic of naming conventions for carbohydrates. So when you see an OSE ending, oftentimes that's referring to a carbohydrate. Lastly, here with glucose, you're going to see that you have an aldehyde group. Yes, there are many more carbons over here as compared to the other two carbohydrates we just looked at. But here we are just looking at the functional group present, whether it's an aldehyde or a ketone. And this is therefore also going to be an aldose. So aldehyde monosaccharides, meaning monosaccharides that contain an aldehyde, are generally classified as aldoses. Ketone monosaccharides will be classified as ketoses. So the first step is just identify your functional group. The next step is to specify the number of carbons. So as you saw in the previous slide, you can have two carbohydrates that both contain aldehydes, but they contain different numbers of carbons. So it's important to be able to distinguish between the two. So in order to specify that, when your carbohydrate contains 3 carbons, we will call that a triose. 4 carbons is a tetrose. Pentose is 5 carbons, and hexose is 6 carbons. So these prefixes here, tri, tetra, pentose, and hexose, and hex, that is referring to the number of carbons. Then we can just put it all together. So these are the same 3 molecules I showed in the previous slide. So now we just combine the 2 terms. So for glyceraldehyde, we identify first that it has an aldehyde, and therefore it's going to receive the name aldo in front of it. And then it contains 3 carbons, 1, 2, and 3, and that's why it is followed by triose here. So an aldotriose is referring to a carbohydrate that contains an aldehyde group and has 3 carbons. Let's look at ketotriose. Here we identify this is a ketone because it has 2 R groups on either side. And then there is 1, 2, and 3 carbons. That's why it's a ketotriose. Here we have an aldehyde, so aldo will be in the front of the name. And then 1, 2, 3, 4, 5, and 6. So hexose after that. We can go ahead and apply what we just learned. So again, we're going to classify these by the type of the carbonyl group and the number of carbons in the chain. So I first identify my carbonyl group. This is an aldehyde. Therefore, I will write aldo in front of it. And then I have 1, 2, 3, 4, 5 carbons, and therefore it's going to be pentose. Triose, I recognize it has an aldehyde here. So it's going to receive the name aldo, and then it's 1, 2, 3, and 4. So that will be tetrose. Lastly, I observe here I have a ketone, and then 1, 2, 3, 4. So ketotetrose. And this is how we can apply general classifications or general names to classes of carbohydrates. Here's some examples of the most common types of monosaccharides. We're going to see that hexoses and pentoses, meaning carbohydrates that contain either 6 carbons or 5 carbons, those are going to be the most common types of monosaccharides. Some examples are glucose, which is a monosaccharide. This is the one that we call blood sugar, and it's shown here. This is the one that is most commonly present in your blood or in high abundance in your blood. And you'll notice that it has 1, 2, 3, 4, 5, 6 carbons, and it is therefore an aldohexose. Galactose is another common monosaccharide. It's one of the components of the disaccharide. So there are 2 monosaccharides together, and it's in lactose. So one of those monosaccharides is going to be this one, galactose. So here we see that it has 1, 2, 3, 4, 5, 6. So, and also it has an aldehyde. So this is also an aldohexose. Lastly, we have fructose, which is one of the components of sucrose. So sucrose, again, is going to have 2 monosaccharides in it, one of which is fructose. And if we count the carbons, we see that there are 6. It's also a type of hexose, but it's going to be a ketohexose because of this ketone functional group. Okay, so that's how we can classify our carbohydrates as mono, di, and polysaccharides. And then we can also name them as aldohexoses or ketohexoses and so on, which will tell you some information about the functional group that's present and then how many carbons it has. But notice in these names here, there's also a prefix shown here, which is the prefix D. This is also part of how we name our compounds. But in order to be able to understand what this D means, we first need to be able to look at the structure of these monosaccharides. And in order to do that, we are going to use Fischer projections. The Fischer projections are just a way to represent these carbohydrates. And what they do is they take a 3D tetrahedral shape, because again, recall that your carbons are going to have 4 bonds to it in a tetrahedral shape. And then it redraws it as a cross formula, as shown here. So first, let's look at our tetrahedron. So let's say I have my carbon, and then again, these wedges here, these solid wedges, that means that the groups Z and X are coming towards you, and the groups W and Y are going away from you. So when we draw this into a Fischer projection formula, the horizontal line, this line here, is assumed to be pointing towards you. So the X and the Z are basically on those wedges. And then the vertical line, so this will be towards you. And then the vertical line means that they are going away from you. But we can communicate that information by just drawing a two-dimensional cross formula as shown here. The other thing to note is that in this cross section right here, in this cross, there is implied a carbon. So this carbon here, so when you interpret these Fischer formulas, you want to recognize that in this cross here, there is a carbon in there, and the X, W, Z, and Y groups are bonded to that carbon. That's not going to be just any carbon, however. It's going to be a carbon that is a chirality center. So a carbon is chiral if it is bonded to 4 different groups. So here, as I've shown in this example, the carbon in this Fischer projection is bonded to X, W, Z, and Y, which are all different groups. And because they are all different groups, this is going to mean that the orientation matters, because whether X is pointing up or pointing back is going to give me different stereoisomers, which we're going to talk about next. Another thing to note is that all carbohydrates have at least one chirality center. So they will have one or more chirality centers. In this slide here, I am showing a molecule that has just one chirality center. But what if I have more than one? What would that look like? So glucose would be an example of a carbohydrate that has more than one chirality center. So let's look at that. So here on the left-hand side is how we have been drawing our structures. And now we're going to start looking at them in these Fischer projections. And again, the important part here is that these crosses are going to be your chirality centers. So let's see how we can identify them. So again, the definition of a chirality center is a carbon that is bonded to 4 different groups. So this first carbon here, it is not bonded to 4 different groups. It's bonded to 3, so it is not considered a chirality center. This next one here in blue, it is bonded to 1 group up here, a hydrogen, this entire other group here, and then an OH group. So all 4 groups are different that are bonded to this carbon. Therefore, this carbon is going to be a chirality center. Therefore, the orientation of where the OH and the H are in the other groups, that is going to matter. Okay, so that's why this one in the Fischer projection is going to look like a cross. So if we continue down the chain, we see that every time we look at a carbon, each group that is bonded to that carbon is different. None of the groups are identical. And that is the case for all of the carbons until you get to the very last one, where you're going to see that this carbon has 2 hydrogens bonded to it, 1 OH, and the rest of that group. So because it has 2 hydrogens, that means this carbon does not have 4 different groups, since 2 of them are hydrogens. Therefore, this carbon is not a chirality center. And therefore, in the Fischer projection formula, it does not receive a cross. You just write it as a condensed formula. So because these are chirality centers and you have 4 different things around these carbons, that means that depending on where they are facing, it is going to give you different molecules. That's why whether the OH groups are drawn on the left-hand side or on the right-hand side, those are going to have meaning in a Fischer projection, because your Fischer projection is communicating a spatial organization. So in order to understand that just a little bit more, we need to revisit isomers. What do I mean by the chirality centers having different orientations or spatial organization? So let's recall what isomers mean. Isomers are basically 2 molecules that have to have the same chemical formula. But then we can divide isomers into 2 categories. We can divide them into constitutional isomers and stereoisomers. We've talked about constitutional isomers. Another way to think about it is as structural isomers, meaning that their structures are different. So that constitutional isomers are going to be molecules that have different bonding patterns. So they are completely different molecules. Their bonding patterns are not the same, but they do have the same chemical formula. So we refer to those as constitutional isomers. Then we talked about stereoisomers, where we looked at a specific type of stereoisomer, which was a diastereomer. So stereoisomers can be divided into two classes. And the one we talked about was this one down here, which was the cis-trans isomers. We saw this when we were dealing with alkenes, where if we had the same carbon groups, where if we had carbon groups on the same side of the double bond, that was cis. If they were on opposite sides, that was trans. So this was a type of stereoisomer. Now we're going to learn about a new type of stereoisomer, which is applicable to carbohydrates, which are called enantiomers. So a definition of enantiomer is basically two compounds with the exact same connectivity. So that's why they fall under stereoisomers, meaning their bonding patterns are the same. That's what we mean by same connectivity. But they are mirror images of each other, and they're not superimposable. So this is going to be the main difference between the other type of stereoisomer we've talked about, which is the cis-trans isomers. These are not mirror images of each other. Enantiomers will be mirror images of each other. An example of that is shown here. I will just say we are not going to discuss these types of stereoisomers, and so we are just going to talk about enantiomers. So why are these mirror images of each other, these two molecules? So if you think of having a mirror here in between these two, you're going to see that this fluorine is reflected on the mirror, and it's going to be the closest one in the reflection. Then Cl will be on this side, Br is on the far back side, and then the hydrogen up here. And so visualize a mirror here in between and what the reflection of this molecule would look like, and that reflection basically is drawn on the other side. So if you try to rotate these two molecules and try to superimpose them, you will see that they are not superimposable, meaning that the fluorine, the chlorine, and the bromine, they are all in different orientations relative to this hydrogen, for example. So if I were to rotate this, they would not all line up together. That's what we mean by it not being superimposable. Okay, so that's what an enantiomer is. It is a type of stereoisomer. So let's see how that applies to a carbohydrate. Because recall that in your carbohydrate, you're going to have carbons that have 4 different groups attached to it. So if you take the reflection of it, then you're going to end up with a molecule that is a mirror image, but it is not superimposable, just like these two molecules here. So let's see how that applies to glucose. Okay, so monosaccharides are going to have enantiomers because they have those chirality centers, meaning they have carbons that have 4 different groups bonded to it. Because they have these enantiomers, we have to distinguish when we name them which enantiomer we are talking about. So we are going to use the D or the L prefix to distinguish that. And we're going to see in a minute how to write that. One thing to note is that all naturally occurring sugars or carbohydrates are going to be D carbohydrates. And we'll see in a minute what that means. Okay, so first, let's go ahead and take our glucose and reflect it over a mirror and get its reflection or its mirror image. So this is the Fischer projection of glucose. Again, each one of these crosses is going to be a carbon, and each one of those carbons has 4 different groups bonded to it. So when we start to take the mirror image, again, this group up here is not a chiral center, so it's not going to receive a reflection. However, this carbon is a chirality center, so we're going to write the reflection on the other side. This OH is closer to the mirror, so that's why this OH is present here. And so we are just drawing its reflection. And then if you're looking at this, the reflection of this molecule in this mirror, you would see that the H is farther away from that mirror, which is why we put this H farther away from the mirror. So you can see the reflection on either side. Basically what is happening is that at every chirality center, the OH and the H groups are switching sides because that's what a reflection does. So if we look at this chirality center here, this OH was on the right-hand side, this one was on the left-hand side. Now if we look at this molecule, the OH is on the left and the H is on the right. So again, we continue to do that until we get to this carbon, which is not a chirality center, which is why it looks the same on either side. Okay, it doesn't get reflected, or it doesn't get flipped. Okay, so that is how we can draw the mirror image of a carbohydrate using Fischer projections. Now, whether the OH is on the right-hand side or on the left-hand side, that is going to matter. Okay? This is what we are going to use to define whether something is a D or an L. So what we do is we go to the very last carbon on these sugars, the very last chiral carbon, not this one down here. So we go to the very last chiral carbon, and then we look, is the OH on the right-hand side or is it on the left-hand side? And this is what we use to label a sugar as a D sugar or as an L sugar. So that is why this compound here, this glucose here, is going to get the D glucose because this OH is on the right-hand side. This glucose is going to get an L in front of it because the OH is on the left-hand side. One way to remember this is that if it's on the left-hand side, it gets the L, and then the OH would then on the right would get the D. Okay, so I want to emphasize here that the reason these two are enantiomers of each other, the reason both are glucose, is because every single chiral center here is reflected on this other side. Every single one is a mirror image of the other. So every single chiral center must be a mirror image of the other in order for them to be enantiomers by definition. So let's apply that. We're going to draw the enantiomers of each monosaccharide as a Fischer projection. And then we're going to designate all molecules as D or L enantiomers. So let's start with glucose here on the left-hand side. I have my mirror, so I'm going to use a dashed line to symbolize that mirror, just to help me draw the Fischer structure. Okay, so first I'm going to identify the carbons that are not chiral centers because those are not going to be reflected in this mirror. So that means this aldehyde group is going to remain the same. And then this CH2OH group is also not a chiral center. So I'm just going to write it in. Now my chiral centers, these here, are the ones that are going to be reflected or flipped, however you want to think about it. So this hydrogen here is going to be reflected on the mirror. So that means it's going to be closer to this mirror on this side. The OH is farther away. You can also think of it as, well, this chiral center, the OH will go to one side and the H will go to the other. So you can continue to do this. Oops. So the reflection here would be HO and H. And that would be the enantiomer because I have reflected every single chiral center in this molecule. So that means this is also going to be a glucose molecule. However, it's going to be either a D or an L. So to determine that, you look at the very last chiral carbon and then determine if the OH is on the left-hand side or on the right-hand side. Here it's on the left-hand side, so this is going to be an L glucose. In this one, it's on the right-hand side, so it will be D glucose. Right, let's do fructose. I'm going to draw my mirror here. So now every carbon that is not a chiral center will stay the same. So that includes these CH2OH groups, and it also includes this carbonyl carbon here. That makes a ketone. Now, all of these other ones, which are crosses, that tells me, the Fischer projection tells me that all of those are chiral centers. All right, so the H is going to be closest to the mirror, and the OH will be farther away. Then this HO is closer to the mirror, and this one goes away, and so on. So this is also fructose because I flipped every single chiral center. Therefore, it is still fructose. It's just going to be a different enantiomer. So for the first fructose here, the OH is on the right-hand side, so that's going to be a D fructose. This one's on the left, so this will be an L fructose. Okay, so that is how we can classify and name monosaccharides. So the classification was basically the monosaccharides, the disaccharides, and the polysaccharides. We will talk about the disaccharides and polysaccharides in another video. This video focused mostly on monosaccharides. We also learned how to name them. Again, just either naming it as an aldo or a keto type of sugar, so an aldose or a ketose. And then we also defined the number of carbons in it as a triose, tetrose, hexose, and so on. Then we looked at how to start drawing their structures. We specifically looked at Fischer projections, where we had to talk about enantiomers because these carbohydrates contain what we call chirality centers. And chirality centers are defined by carbon being bonded to 4 different groups. Okay. In the next video, we are going to look at how to draw Haworth projections or Haworth projections. Now that we have learned how to draw the open chain, which is just a Fischer projection, we're going to learn how to then go from a straight chain, as shown here on the left-hand side, into something that is cyclic. And the reason we want to do this is because it's going to be these cyclic structures that are going to end up forming the disaccharides and the polysaccharides that we will also talk about later.